Hello everyone, I hope you're all doing well. In this video I'm going to go through how to find the shortest distance between two vector lines in 3D. So whether those lines are parallel or skew. So they're lines which don't intersect, because of course if they do intersect, the shortest distance between them is 0. So we're going to start off with skew lines, and just a reminder, when you have two lines in a 3D space, they can be parallel, like I'm holding these now, so they could be at any angle but parallel, or they could be skew, which means they don't intersect, they are not parallel, and we can find out the shortest distance between them. Now what we do know is that the shortest distance will meet each line at 90 degrees. And therefore, because they meet each line at 90 degrees, I already know that if I did the dot product between one of the lines and the shortest distance between them, I know perpendicular lines have a dot product of 0. So this will certainly be coming in. So I'm going to start off, I'm going to call this A and call this B. So A will be a general point on line L1. And the general point we're going to call, so that would be 1, lambda, lambda. That is a general point, so that is a positional point. And we'll do the same. B will be a general point on line L2. So looking at this line, it would be minus 1 plus 2 mu, 3 minus mu, minus 1 minus mu. Now the key thing is these are both positional vectors. So this is the vector from the origin, a point from the origin to the line. So these are like coordinates. So we know we're going to look for the shortest distance, so we need to know how to move between these two. So I'm going to work out the distance of A to B. Now I can see, how do I get from here to here? Well, I can see I need to take away 2, but then I also need to have this 2 mu appear, so plus 2 mu. All right, the lambda needs to disappear, so I've got to take away that lambda. And then these two need to appear, so that's how I'm getting there. So I've got to get from here to here. Again, the mu lambda needs to disappear, and I need to take away 1 and take away mu. So this is a movement vector. Now, we know the movement vectors will be perpendicular. This distance, if we want it to be the shortest between these two lines, have to meet those two lines at 90 degrees. So that means if I take this movement vector and dot product with, I'm going to start with this line, line 1, and I dot product with this, I know it will come out with 0. So if we do this dot product, we will get minus lambda plus 3 minus mu minus lambda minus 1 minus mu equals 0. So therefore, we end up with, I'm going to just put another bit of paper at the bottom of here, just running out a little bit of space. I want to kind of keep this going. So we'll end up with 2 minus 2 mu minus 2 lambda equals 0. So I'm just going to turn these to the other side and divide them all by 2. So I now know mu plus lambda equals 1. I am now going to repeat this process. So this was me making sure that this movement meets this line at 90 degrees. So now I'm going to make sure that this movement meets this line at 90 degrees. So that means, again, I'll take my movement A to B, and dot product, this time with this movement. And again, this line between has to meet both at 90 degrees. So we will have minus 4 plus 4 mu plus lambda minus 3 plus mu plus lambda plus 1 plus mu equals 0. So again, collecting terms, we've got minus 6 plus 6 mu plus 2 lambda. So just again, I'm going to divide everything by 2, and I'm taking this term to the other side. I now have two simultaneous equations to solve. Now I can solve them algebraically, but you have your calculator in the exam and expected to use it. So for those who've forgotten, we have the solving simultaneous equation mode, and I have the equation 1, 1, 1, and 3, 1, 3. And that would give me mu equals 1 and lambda equals 0. So I now know the shortest vector of A to B will occur when these two are true. So I'm going to go back to my movement and substitute these in. And that would give me, well, mu is 1, so that would be 0. Lambda is 0 and mu is 1. I get 2. And lastly, I get minus 2. So this vector here, we know is the shortest one. So therefore, to get the distance between the two, I am just going to Pythagoras the vector to give me 2 root 2. And that is the shortest distance between these two lines. I'm now going to do a similar thing, but for parallel lines. Now, you can use the exact same method if they're parallel, but there's also a few little shortcuts we can make. So first of all, just like last time, I'm going to let A be a point on the first line, which would be 1 plus 5 lambda, 2 plus 4 lambda, minus 1 plus 3 lambda. And B will be a point on the second line. So therefore, 2 plus 5 mu. I always have to do it the same alphabet. J's missing, so 0 plus 4 mu. And then K plus 3 mu. Now, key thing to notice when they're parallel, of course, we've got 5 lambda, 5 mu, 4 lambda, 4 mu, 3 lambda, 3 mu. Those coefficients will be the same. So that can actually help us. Now, what we can do to save time, now I'm going to do this first and then I'll explain where it comes to. I can say A to B, and I can only do this if it's parallel. So first of all, I do have to check the numbers. So at the beginning, I've got to add 1, take away 2. I think that was a really bad number 1 there. And therefore, I've also got to add 2 here. But what I can do is, and what I'm going to write for the movement part is this. I'll explain why in just a second. Now this, you don't have to do this. You can go through the method I showed you last time. But if it's parallel, I can make that jump. And just to let you know, T is mu minus lambda. So what I actually did there was I did my distance between the two. This bit you don't need to show in an exam. You could just write this. But if they're parallel, again, I'm still going to have the same numbers at the front. But I've got to get rid of this one here, and I'll be adding on this one. Again, removing the lambda, adding the mu, because I've got to get from this one to that one. minus 3 lambda plus 3 mu, which means that is the same as 5 lots of mu minus lambda. So when they're parallel, you will have this occur. But to save you writing all that, you can just jump to here. So we only actually have one variable to find out. Now, so what we've got now, we've got a movement between the two lines. So we know that this line, to be the shortest, has to meet both of them at 90 degrees. So I'm going to take this movement, and it is quite nicer to have one variable rather than two. And I'm going to dot product. Now I only need to do it with one of these. And I know it's 0 because they have to meet at 90 degrees. So we have 1 plus 25t minus 8 plus 16t plus 6 plus 9t equals 0. Now that means we have 25t's equal minus 3. So t is minus 3 over 50. That means when AB is the shortest, I will substitute this back into this equation, and it was shortest when this is the movement. So to find that shortest distance, all I need to do is Pythagoras these values. And that comes out as 21 root 2 over 10. So this is the shortest distance between two parallel lines.